What's up, math lads? So you made it to episode 2 of our abstract algebra curriculum. You know about integers, prime numbers, and learned a fundamental theorem. If you didn't, go watch that video, because otherwise the rest of this might not be good for your health. That's because today we're covering groups. What even are groups? In a basic sense, they're just a set, or collection of objects. This collection is then paired with a binary operation that takes in two objects from the set and outputs another object in that set. So if I take two people that are disappointments and bring them together, they'll create another disappointment. You. There are a couple of rules though. Suppose we have a group G with binary operation star. This could be addition, multiplication, function composition, really anything, as long as it fits the rules. First off, you need associativity. You know that thing that lets you move parentheses around? A plus B plus C should still be A plus B plus C. Second, you need an identity element, usually labeled with the 1 sub G or the letter E, because E isn't already anything significant in math. This object is the do-nothing object. If we combine this element with another one, by means of our binary operation, then we should return the other element. It also shouldn't matter what order we operate in the case of the identity. More on that later. Lastly, we need to know that for every element in the group, there exists an inverse element that when combined with the original element, it returns the identity. In summary, every group should follow up by following the following. You can move parentheses, there exists an identity, and every element has an inverse. So now that we have a framework, let's come up with some examples. Let's talk integers. Integers under addition are a group. If you take two integers and add them, you get another integer. We already know addition is associative. The additive identity is 0, and the additive inverses are negative numbers. That's nice, but what about multiplication? Are integers a group under multiplication? The answer is no, since the multiplicative inverse of almost all integers is a non-integer rational number. You can thank the ancient Egyptians for creating this inconvenience. So groups are actually pretty familiar to us. Now let's explore a weirder one. Dihedral groups are groups that are analogous to geometric symmetries. Let's take an equilateral triangle. An equilateral triangle. We can do 6 things to transform this triangle. We can do absolutely nothing to it, like your parents probably did with respect to supporting your hopes and dreams. You can rotate it 120 degrees, rotate it 240 degrees, or flip it along one of its 3 lines of symmetry. Each of these actions can be described as sending each vertex to a new position. So it's like each transformation maps one set of vertices to another. Where have we heard of maps before? So the transformation of this triangle is a set of functions that always sends the vertices to another orientation of the triangle. So if we chain these transformations together, we could probably describe that in terms of a function composition, which would be a binary operation. If we wanted to visualize this with function diagrams, we could chain them together like this. We would just follow the path and condense it to see which is equivalent to the composition. Let's see if this checks the rules. Is it associative? Yes, because function composition is always associative. Is there an identity? Yes, the do-nothing transformation, where we neglect the needs of the triangle at the expense of its mental health. Are there inverses? Well, if we rotate 120 degrees, then rotate 240 degrees, we get the original triangle. The same as doing nothing, and vice versa if we start with the other rotation. Also, if we flip along a line of symmetry, we could just flip again to get back to where we started. This entire structure is called D6, or the dihedral group of order 6. Notice we haven't really talked about commutativity. Dihedral groups are not commutative, since flipping then rotating is not the same as rotating then flipping. Most matrix groups under standard matrix multiplication are not commutative. Now if a group does have commutativity, like the integers under addition, it is also called abelian, named after this Abel guy, whoever he was, probably not that important. So let's talk some facts about groups that apply no matter what group you're talking about. For starters, A inverse inverse is equal to A. The proof is pretty simple. A is equal to A times the identity, which is equal to A times the quantity A inverse times A inverse inverse. This is equal to A times A inverse times A inverse inverse, because we can reassociate. This is equal to the identity times A inverse inverse, which is equal to A inverse inverse. So A eventually equals A inverse inverse. For now, we're going to define integer exponentiation as repeated multiplication, and these next facts are going to rely on it. Number 1, g to the m times g to the n is equal to g to the m plus n. And number 2, g to the m raised to the n is equal to g to the m times n. This can be shown just by expanding and moving parentheses. Lastly, g times h, the quantity, raised to the n, is equal to h inverse times g inverse raised to the negative n. This can be shown by understanding that h inverse times g inverse is the inverse of g times h. Order matters here, which is why we can't just expand and rearrange elements. Commutativity is not guaranteed. This last one is a little weird, because it goes against our familiarity with integers and real numbers. That being said, you're a real mathematician now. How does it feel? The answer is probably underwhelming, especially since this one guy said this one thing that's probably accurate. So nothing you discover will ever surprise you again. What a wonderful thought to end this video on. Anyways, I hope you liked this video. If you want to see more, please subscribe to the channel and leave any thoughts you have in the comments down below. Thank you for your time and keep learning.